You're about to meet a planet that, by the rules we use right now, really shouldn't exist at all. Astronomers call it PSR J2322-2650b. It sits around 750 light years away from you in the constellation Sculptor, and at first glance it sounds familiar. It has about the mass of Jupiter. So far, so normal. But then you look at what it orbits, and the whole situation stops being normal immediately. But before we continue, please subscribe to the channel to give your support. Let's continue. This planet is not going around a calm, shining, sun-like star. It circles a neutron star, the collapsed, ultra-dense core left over after a massive star blew itself apart in a supernova. That parent star went through its full life cycle, burned through its fuel, exploded violently, and then collapsed into a tiny, compact object with more mass than the sun squeezed into a body the size of a city. In that blast, most nearby material should have been stripped, heated, or just thrown out of the system. Yet, somehow, you still have this Jupiter mass object sitting in a tight orbit. Either it survived the supernova, which is already hard to make work with our models, or it formed afterwards out of the wreckage, which is also extreme. In both cases, you're looking at a world that has lived. You're about to meet a planet that, by the rules we use right now, really shouldn't exist at all. Astronomers call it PSR J2322-2650b. It sits around 750 light years away from you in the constellation Sculptor, and at first glance it sounds familiar. It has about the mass of Jupiter. So far, so normal. But then you look at what it orbits, and the whole situation stops being normal immediately. But before we continue, please subscribe to the channel to give your support. Let's continue. This planet is not going around a calm, shining, sun-like star. It circles a neutron star, the collapsed, ultra-dense core left over after a massive star blew itself apart in a supernova. That parent star went through its full life cycle, burned through its fuel, exploded violently, and then collapsed into a tiny, compact object with more mass than the sun squeezed into a body the size of a city. In that blast, most nearby material should have been stripped, heated, or just thrown out of the system. Yet, somehow, you still have this Jupiter mass object sitting in a tight orbit. Either it survived the supernova, which is already hard to make work with our models, or it formed afterwards out of the wreckage, which is also extreme. In both cases, you're looking at a world that has lived its entire existence in a place that should be hostile to planets, with a host star that is effectively a stellar corpse. That's why astronomers sometimes call this kind of object a problem for theory. The usual picture says planets grow quietly in a disk of gas and dust around a young, normal star. Here, the star is not young and not normal. The environment has been blasted by one of the most violent events in the universe, and somehow a planet-mass body is still there, close in and bright enough in infrared that James Webb Space Telescope can study it. Already, this planet is telling you that your picture of where planets can live is too limited. But the weirdness doesn't stop with where it is. The next thing that hits you is how it moves through time. If the environment is that extreme, what does a year even mean here? On this planet, a full year lasts about 7.8 hours. Not days, not weeks, hours. In the time it takes you to wake up, go through a long workday, and get ready for bed, this world has completed one full orbit around its sun. For you, 8 hours is a shift. For this planet, 8 hours is an entire trip around its sun. The distance of that orbit is about 1.6 million kilometers, roughly 1 million miles. For comparison, Earth orbits the sun at about 150 million kilometers, roughly 93 million miles. So this planet is around 100 times closer to its star than you are to yours. In more familiar terms, that separation is only about 4 times the distance between Earth and the Moon. You are used to seeing the Moon as very close on the cosmic scale, and this world is only a few lunar distances away from a neutron star. At that range, orbital speeds are extreme. The planet is racing around so fast that if you could somehow ride along just above its cloud tops, you'd be moving at hundreds of kilometers per second, hundreds of thousands of miles per hour. That tight orbit is also not a gentle place dynamically. The gravitational pull changes very quickly as you move around, and the star's influence is intense over that short distance. So, you've got a Jupiter mass body crammed into a tiny orbit, circling a dead, compact star in less than one workday. That alone would make this system remarkable. But if you force a planet that close to something that dense, you have to ask, does it even stay round anymore, or does gravity start to reshape it? That's where the shape of this planet becomes another problem. Under normal conditions, large gas giants end up almost perfectly spherical because their own gravity pulls material equally in all directions. Here, the neutron star's gravity is so strong and the difference in pull between the near side and the far side is so large that the planet gets physically stretched. Instead of a neat, almost perfect ball, this planet is distorted into a lemon or rugby ball shape. The numbers people use are straightforward but brutal. The equatorial diameter is estimated to be about 38% larger than the distance from pole to pole. That is not a small adjustment. That is a massive deformation. On Earth, you see tidal forces as ocean tides. The moon lifts the water for a few meters, maybe a bit more in extreme locations. The solid Earth itself flexes slightly, but you don't really notice it. Here, the whole planet is the tide. Gas in the atmosphere, deeper layers of fluid, probably even the internal structure are constantly being pulled along the axis connecting the planet and the neutron star. The gravitational pull on the side facing the star is noticeably stronger than the pull on the far side. That difference is what stretches the planet, and its own self-gravity is just barely enough to keep it from being pulled apart entirely. It's sitting close to what's called the Roche limit, the distance where an object held together only by its own gravity starts to break apart. This planet hasn't crossed that line yet, but it's near enough that you can see the effect in its global shape. So now the system is even more disturbing. You don't just have a planet in a harsh orbit, you have a world that is being physically reshaped by its star's gravity, squeezed along one axis and stretched along another. That leads to a natural next question. How do we know any of this with confidence when this system is so far away and the host star is such a strange object? This is where this planet becomes a perfect test for Webb, even though the telescope was never designed specifically for pulsar planets. Normally, the hardest part of studying an exoplanet is the host star. A sun-like star is incredibly bright and visible in infrared light, and the planet is tiny and faint in comparison. You have to subtract the star's light very carefully or block it entirely just to see a tiny signal from the planet's atmosphere or its temperature. Here, the situation is flipped. The host is a neutron star, a pulsar, that emits most of its power in radio waves, X-rays, and gamma rays. Those are extremely energetic and extremely dangerous for nearby matter, but Webb is not very sensitive to them. It is built to see infrared light, the kind of glow that comes from warm dust and hot planets. In infrared, the pulsar is relatively faint, while this planet, with dayside temperatures over 2,000 degrees Celsius, shines strongly. That means Webb can watch this system without being overwhelmed by the star. By tracking the infrared brightness over the full 7.8-hour orbit, astronomers build what's called a thermal phase curve, a record of how the observed heat output changes as different sides of the planet rotate into view. When the hot day side faces us, the signal rises. When the cooler night side faces us, it drops. When the planet passes behind the pulsar from our point of view, there is a small dip that lets scientists isolate how much light comes from the planet alone. On top of that, Webb spectrographs split that infrared light into many wavelengths. Each molecule in the atmosphere absorbs and emits at very specific wavelengths, like unique fingerprints. In this planet's case, those fingerprints show strong helium and exotic carbon molecules, and very weak or missing signatures from familiar oxygen-bearing species like water vapor and carbon monoxide. That already tells you that this is not a standard hot Jupiter that just migrated inward. It is something chemically different. So, in one system, you have a Jupiter mass object in an orbit of only 7.8 hours at a distance of about 1.6 million kilometers, stretched into a lemon shake by tides, blasted by high-energy radiation, and glowing so hot that Webb can read its atmosphere from across the galaxy. All of that is already pushing your idea of what a planet can be. But this is only the start. To really feel how extreme this environment is, you need to look at the central object itself, the thing acting as this planet's sun, a neutron star only about the size of a city, spinning hundreds of times per second and controlling everything in this system with its gravity and radiation. How do you orbit a star that's only about the size of a city, but has more mass than the sun and spins hundreds of times every second? That's the setup here. This planet is not circling a normal sun, it's locked to a compact object called PSR J2322-2650, and that star is the real monster in this system. Your sun here is a neutron star only about 10 to 20 kilometers across, so roughly 6 to 12 miles, which is smaller than many cities you know. But inside that tiny volume, you pack around 1.4 times the mass of the sun. You take something with the mass of about 2 quadrillion tons and you crush it into a ball you could drive around in half an hour. The surface gravity is so intense that if you could stand there, which you can't, you'd be dealing with hundreds of billions of G or more, basically instant death for any normal matter. On top of that, this neutron star is spinning once every about 3.5 milliseconds. That's nearly 300 full rotations every second. If you translate that into a more familiar measure, that's over 18,000 revolutions per minute. A car engine at 6,000 RPM is screaming. This thing is doing 3 times that, and it's a star. This spin is not gentle. It drags the star's magnetic field and its particle environment around with it, like a rigid structure locked to the crust. This is why you hear the term millisecond pulsar. It's a neutron star that has been spun up over time, usually by pulling matter off a companion until its rotation period shrinks into the millisecond range. Every turn, it sweeps beams of radiation past your line of sight, and you see them as very regular pulses in radio waves or higher energy bands. So when you call PSR J2322-2650 the sun of this planet, you're really talking about a 10 to 20 kilometer wide, ultra-dense, ultra-fast rotor that never stops. So what exactly is this thing made of, and why is it so extreme compared to anything you're used to calling a star? You're dealing with the leftover core of a massive star that went supernova. In its earlier life, this object was probably several times the mass of the sun. It burned through nuclear fuel, built heavier and heavier elements in its core, and eventually collapsed under its own weight. The outer layers were thrown off in a supernova explosion. The inner core, with more than a sun's mass, collapsed into a neutron star. In that collapse, electrons and protons in the core are squeezed so hard that they merge into neutrons. You end up with matter so dense that a teaspoon of it would weigh hundreds of millions of tons. That's not an exaggeration. That's the literal density scale you're dealing with. The crust is a solid lattice of nuclei. Deeper down, you get a super dense fluid of neutrons and possibly even more exotic phases of matter that we still don't fully understand. The magnetic field is also on another level. A neutron star can have a magnetic field trillions of times stronger than Earth's field. As PSR J2322-2650 spins, this magnetic field acts like a gigantic generator. Charged particles are ripped away from the surface and accelerated to near light speed along magnetic field lines. That process creates beams of radiation, not in friendly visible light, but in radio waves, X-rays, and gamma rays. So because the magnetic poles are not perfectly aligned with the spin axis, those beams sweep around as the star rotates. If one of those beams crosses Earth, you see a pulse every time it spins, like a very precise ticking clock. The timing is so sharp that you can measure changes of microseconds over years. This is why pulsars are used as cosmic clocks. But for this planet, that clock is also a constant radiation source. If the star is this dense, this fast, and this radioactive, why would you expect any planet to survive close to it in a tight orbit? In general, you don't. Pulsar winds are streams of high-energy particles moving at relativistic speeds, a significant fraction of the speed of light. Those particles slam into anything nearby with huge energy, breaking molecules, stripping atmospheres, and heating surfaces. On top of that, the neutron star's gravity field is very steep. Farther out, space looks normal. But as you move in, the difference in gravitational pull from one side of an object to the other grows quickly. Any loosely bound structure, like a normal gas giant, should struggle to stay intact if it gets too close. That's why the idea of a planet in a tight orbit around the pulsar sounds wrong on first pass. We do know a few pulsar planets. The first exoplanets ever discovered were around the pulsar called PSR B1257+12. But those are usually low mass, closer to Earth or super-Earth scale, and likely formed from leftover debris or fallback material after the explosion. A Jupiter mass companion in a very tight orbit is not the default outcome. It's more common in our models for that much mass to end up as another star or to be stripped down or ejected entirely. So when you see a system where a gas giant mass object is sitting only about 0.01 astronomical units from a neutron star, you're looking at something that has already broken several expectations. Just from the presence of this planet alone, you know this system has gone through a very unusual history. Either the planet is the hyper-stripped core of a former star, or some exotic formation process built a planet mass body in the middle of a radiation storm. That brings you to the next question. If the environment is that violent, what does it actually feel like for the planet to sit inside that radiation bath every orbit? Webb can't see the pulsar directly the way it sees normal stars. The neutron star's main output is in gamma rays and X-rays, plus the high-energy particle wind. Those bands are outside Webb's infrared range, so in its detectors, PSR J2322-2650 is not a bright, blinding object, but the planet is constantly immersed in that high-energy environment. It's like living inside the spill zone of a particle accelerator. Every square meter of the dayside is being hit by streams of particles and bursts of hard radiation far more intense than the sunlight hitting Earth. That energy doesn't show up directly in Webb's cameras, but it shows up indirectly in what it does to the planet. It heats the atmosphere, drives chemistry, and strips lighter elements away over long timescales. Because the orbit is so tight, the planet is almost certainly tidally locked, with one hemisphere always facing the neutron star. That permanent dayside is the side that takes the full blast of radiation and particle wind. The night side, facing away, still gets heated by redistributed energy, but is shielded from direct impact. The result is a world where one side is a constant target and the other side acts like a sort of reservoir. The key point here is simple. Under this kind of assault, a normal gas giant atmosphere with lots of hydrogen, oxygen, and nitrogen should be heavily stripped or reshaped. The fact that an atmosphere still exists and that it has the weird helium-carbon-dominated chemistry that Webb picks up is a major clue. It says this is not just a planet that wandered too close. It's very likely the leftover core of something much bigger, with deeper layers rich in helium and carbon that can keep feeding the outer envelope even as the pulsar tries to erode it away. So now you have the full picture for the star side of the system. The Sun is a 10 to 20 kilometer wide neutron star, heavier than the Sun, spinning nearly 300 times per second, blasting out particle winds and high-energy radiation. The planet is parked uncomfortably close, just outside the zone where gravity and radiation would completely destroy it. And somehow it's still there, still glowing, still holding on to an atmosphere. That sets up the next problem you need to unpack. If this is the host and this is the environment, what does that insanely tight orbit actually do to the planet's motion, its stability, and its long-term survival? When it's moving through the kill zone of a neutron star every single hour of its year? How dangerous does an orbit have to be before you stop calling it stable and start calling it a slow-motion execution? That's basically the situation for this planet. It doesn't just orbit close to its neutron star, it lives in what is basically the kill zone, and it completes that orbit in about 7.8 hours. Think about that pacing for a second. On Earth, 7.8 hours is a long work shift, or a flight that feels like it will never end. For this planet, that same chunk of time is a full year. From New Year's to New Year's again, less than 8 hours. In that period, it whips all the way around a neutron star that's only about 10 to 20 kilometers across, roughly 6 to 12 miles. To do that, the planet has to move at insane speeds. You're talking roughly 350 kilometers per second, which is about 780,000 miles per hour. For comparison, Earth cruises around the sun at about 30 kilometers per second, somewhere near 67,000 miles per hour. So this planet is doing more than 10 times Earth's orbital speed in a tiny, tight loop. If you could somehow stand on its cloud tops, the neutron star would crawl across the sky in slow motion. But that's only because you're locked to the same rotation. Underneath you, the orbital speed is brutal. And here's the important part. This is not just a fast orbit, it's a fast orbit at a distance of only about 0.010 astronomical units, so around 1.5 to 1.6 million kilometers, roughly 1 million miles from the neutron star. That's only a bit more than 4 times the Earth-Moon distance. At that range, the difference in gravity between the near side and far side of the planet doesn't just cause tides, it tries to rip the whole world open. So the next question is obvious. At that distance, is gravity still letting this planet be a planet, or is it already starting to pull it apart? You're basically watching a fight between the planet's own gravity and the neutron star's gravity. The planet wants to stay round, because that's the natural state for a big ball of gas. Its own gravity pulls inward equally from all directions. The neutron star wants to stretch it, because the gravitational pull on the side facing the star is stronger than on the far side. That difference in pull is what we call a tidal force. On Earth, tidal forces lift the oceans by a few meters and flex the solid planet by a smaller amount you don't feel in daily life. Here, the same basic physics is operating at much higher levels. At only about 0.010 AU, the tidal force is strong enough to stretch the entire planet into a lemon-like profile. The equatorial diameter is estimated to be roughly 38% larger than the polar diameter. That is a huge distortion. This is where the concept of the Roche limit comes in. The Roche limit is the distance inside which an object held together only by its own gravity can't survive intact. If you push a planet inside that limit, the gravitational pull from the star becomes stronger than the planet's self-gravity pulling it together, and the object gets torn into pieces. Those pieces can spread out into a ring of debris. This planet is just outside that shredding zone. It hasn't crossed the Roche limit, but it's close enough that you see the warning signs all over its structure. The outer layers are under constant stress, and the planet is on the edge of becoming something like a ring system instead of a single body. In other words, this is not a comfortable orbit, it's a barely allowed one. So if it's that close to disaster, what does daily life look like for the planet itself in terms of how it spins and how heat is spread around? At this distance, you can pretty much guarantee that the planet is tidally locked. That means it always keeps the same face pointed at the neutron star, just like the moon always shows the same face to Earth. One hemisphere is in permanent day, staring straight at a compact star that's firing out high-energy particles and radiation. The other hemisphere is in permanent night, never seeing the star directly. That doesn't mean the night side is cold and comfortable. The whole planet is so close to its host that even the dark side is a furnace. The day side is a full-on inferno, with temperatures climbing over 2,000 degrees Celsius, more than 3,700 degrees Fahrenheit. The night side is still around 600 to 700 degrees Celsius, over 1,000 degrees Fahrenheit, hotter than an industrial pizza oven. Tidal locking also links the orbit and the spin. Over long timescales, the same gravitational interactions that lock the rotation start to sap orbital energy. The planet raises tides on the neutron star too, in a very small way, and those tidal forces exchange energy and angular momentum between the orbit and the spin. In many hot Jupiter systems, that process can slowly move a planet outward or inward, depending on the details. Here, given the extreme gravity and tight orbit, the long-term trend is likely inward. You can think of it as a very slow tightening of a noose. Each orbit, the system loses a tiny bit of orbital energy to heat and tidal friction. Over millions to billions of years, that can shrink the orbital radius, pushing the planet closer to the Roche limit. At some point, if nothing else changes, it could cross that line, and then the planet doesn't just deform, it starts to break up. So this is a world with no sunrises and no sunsets, a permanent dayside facing a neutron star, a permanent nightside still baking, and an orbit that slowly wants to pull it closer to destruction. That alone is dark enough, but there's another layer that makes this orbit even more unsettling. It doesn't fit our standard ideas for how such a system could form in the first place. Gas giants are not supposed to form this close to their stars. In the early stages of a star system, the region very close to the star is too hot and too turbulent for gas giants to build up. They normally form farther out, where ices and gas can accumulate into a massive core and envelope. Then, some of them migrate inwards later, through interactions with the gas disk or with other planets. If this planet had followed that standard route, you'd expect a few things. You'd expect certain patterns in its orbit, and you'd expect a roughly normal hot Jupiter chemistry, with hydrogen and helium dominant, plus water vapor, carbon monoxide, methane, and other molecules with oxygen and nitrogen. You might see those molecules broken up or reshuffled by temperature, but the basic element ratios would still look planet-like. Instead, what you see here is an orbit that's so tight and a chemistry that's so skewed towards helium and carbon that the usual migration story doesn't fit cleanly. It's hard to get a fully ordinary gas giant into this orbit without destroying it, and it's hard to erase oxygen and nitrogen that completely if it started with standard planetary composition. The simpler explanation, even though it sounds more extreme, is that this planet is not a normal planet at all. The orbit and the chemistry together point toward an origin where this object used to be part of a star. Its current path at about 0.010 AU, just outside the Roche limit, and its weird helium-carbon atmosphere are both easier to explain if you say this was once a full-size companion star that got stripped down by the neutron star's radiation and gravity. So when you look at this orbit, you're not just seeing a fast, tight trajectory. You're seeing the final track of a former star, shaven down to planet mass, held just above the breaking point and still slowly losing ground. That thought leads straight into the next question. If gravity is strong enough here to reshape a former star into a lemon-shaped planet, what exactly is happening inside this object second by second as those tidal forces squeeze, stretch, and heat it from the outside in? How far can you push a planet before gravity stops just shaping it and starts trying to unbuild it from the outside in? That's the situation here. This planet is a live test of how much stress a Jupiter-mass world can take when you drop it about 1 million miles, roughly 1.6 million kilometers, from a neutron star with around 1.4 times the sun's mass. Here's the basic setup. On the side of the planet facing the neutron star, gravity pulls a little harder. On the far side, gravity is slightly weaker. Over the whole diameter of the planet, that difference in pull becomes huge at this tiny distance. That gradient is the tidal force. It's the same kind of effect that lifts oceans on Earth, but here you apply it across a gas giant that's hugging a compact star. The result is that the planet's own gravity can't keep it perfectly round. Because of that constant pulling, the planet's shape is stretched along the line pointing toward the neutron star and squeezed in the directions perpendicular to that. Observations and modeling suggest the equatorial diameter is roughly 38% larger than the polar diameter. For a Jupiter-sized object, that means the long axis is tens of thousands of kilometers, tens of thousands of miles, bigger than the short axis. That's not a cosmetic tweak. That's a deep structural distortion enforced by gravity every second of every orbit. So if this is the extreme case, what does that tell you about the kind of tides you'd feel on a world like this compared to the gentle tides you see on Earth? On Earth, the moon lifts our oceans by a few meters, maybe a few tens of meters in the most extreme cases. The solid crust flexes a little too, but not in a way that changes Earth's overall shape in a dramatic way. The main thing you notice is water moving in and out along coastlines. The moon is far away, and Earth is relatively rigid and massive compared to its tidal pole. Here, the numbers flip. This planet is only about 4 Earth-Moon distances from a neutron star that is heavier than the Sun. The difference in gravity across its body is enormous. The entire planet is the tide. The gas, the deeper layers, the clouds, everything is being pulled into a rugby ball shape aligned with the direction toward the neutron star. There isn't a calm rest shape that it returns to. It's always under this tension, all the way through. You can think about this stress this way. In one direction, along the line toward the neutron star, material is being pulled outward, away from the planet's center. And the perpendicular directions, material is being squeezed inwards. That means the internal structure is under constant shear, constant stretching and compressing as the world orbits. And because the orbit is not perfectly circular and the planet's interior is not perfectly uniform, those tidal forces change slightly over time, leading to constant flexing. So the next question is, if you keep flexing a whole planet like that, orbit after orbit, what happens to its internal energy and stability? When you repeatedly flex any material, you generate heat. On Earth, you see a milder version of this in places like Jupiter's moon Io, where tidal forces from Jupiter and the other moons constantly squeeze and relax the moon's interior. That flexing turns orbital energy into heat, driving intense volcanism. On this planet, the same principle applies, but scaled up to a much heavier object in a far stronger gravitational field. The tidal forces don't just change the external shape, they pump energy into the interior. Layers of gas and denser material get dragged back and forth. Friction between layers converts that motion into heat. That heat rises toward the outer atmosphere, adding to the energy the planet receives from the pulsar's radiation and particle wind. It helps explain why the dayside temperature can hit above 2,000 degrees Celsius, around 3,700 degrees Fahrenheit, and why the night side is still above 600 degrees Celsius, over 1,000 degrees Fahrenheit. Inside, this constant stress can stir up powerful convection, giant circulation cells that move hot material upward and cooler material downward. It can also create internal waves and oscillations where whole regions of the interior shift in response to changing tidal forces. Over long periods, that can change how the planet's interior is layered, how angular momentum is distributed, and even how the magnetic field behaves if there's a conducting region. You're not looking at a quiet, stable gas ball. You're looking at a body that is being mechanically worked by gravity all the time. If gravity is already strong enough to squash this planet into a stretched shape and heat its interior, where's the line where it stops being able to hold together at all? That line is the Roche limit. Outside the Roche limit, an object held together by its own gravity can stay intact, even if it's distorted. Inside the Roche limit, the tidal forces from the central body become stronger than the object's self-gravity. At that point, regions on the near side and far side are pulled away faster than the object can pull them back in. Material starts to escape and spread along the orbit, forming streams and rings. For a Jupiter giant around a compact 1.4 solar mass neutron star, the Roche limit sits only slightly inward of where this planet currently orbits, at about 0.010 astronomical units, about 1.5 to 1.6 million kilometers, roughly 1 million miles. Right now, the planet is outside that limit, but not by a comfortable margin. Its lemon shape is a sign that the internal gravity is just barely winning over the tidal pole. If you move this planet a little closer, even by a fraction of that distance, the balance would shift. Regions in the outer atmosphere would be stripped first, then deeper layers would follow. Instead of a single distorted body, you'd start to get a torus or ring of gas and dust orbiting the neutron star. Over time, that ring could thin out, fall inwards, or be blown away by the pulsar wind, leaving only remnants. That's why this system feels like it's parked on the edge of a cliff. The current orbit is already causing major deformation and heating, and over long timescales, tidal interactions and mass loss can gently nudge the planet inwards. There's no need for a sudden catastrophe. Tiny changes per million years are enough. At some point, if nothing else changes, one side of that balance will win, and the planet will cross from barely holding together to slowly turning into a ring of debris. So you have a Jupiter mass object, distorted by tides so strongly that its equator is about 38% wider than its poles, heated from the inside by constant flexing, and sitting just outside the distance where gravity would tear it apart completely. That's already extreme on the structural side. But there's another layer of brutality here. When you take a planet, squash it, heat it from the inside, and park it in front of a neutron star's radiation and particle wind, you don't just get a weird shape. You get a climate that barely fits into normal categories, with temperatures and conditions that make most stars look mild by comparison. This planet's dayside is so hot that a lot of things you think of as solid objects would behave more like soft wax. The permanent day hemisphere sits at roughly 2038 degrees Celsius, around 3700 degrees Fahrenheit. At those temperatures, many metals soften, some start to melt, and rock itself is close to its melting point. You're not dealing with a warm gas giant here. You're dealing with something hotter than the surface of many red dwarf stars, where hydrogen fusion is actually happening in the core. Because it's so close to the neutron star, only about 1.6 million kilometers away, roughly 1 million miles, the planet absorbs a huge amount of energy every second. On top of that, tidal forces are adding more heat from the inside, as we just went through. All of that energy has to go somewhere. The result is an atmosphere that glows very strongly in infrared. To Webb, this planet is not a faint dot. It's a bright source of thermal radiation, like very hot metal that has just come out of a furnace. At these temperatures, the usual picture of clouds and weather that you have from Earth completely breaks down. Any normal water or ammonia in the upper atmosphere is gone, broken apart or driven off. Instead, the weather is about how gas flows at thousands of degrees, and how that gas moves heat from the dayside to the nightside. The baseline is simple. The dayside is a continuous high-temperature zone with no relief, no night, and no cool mornings. So if the side staring at the neutron star is that extreme, what does night even mean on the far side of a world like this? And does anything ever really cool down there? The night side is technically cooler, but that word stops being comforting when you look at the actual numbers. The dark hemisphere sits at roughly 649 degrees Celsius, about 1200 degrees Fahrenheit. That is hotter than a pizza oven, hot enough to melt lead, and far beyond anything you would call livable or even survivable for normal materials over long periods. You might expect the night side to drop toward much lower temperatures because it never sees the neutron star directly. But this planet's atmosphere is not static. Strong temperature differences between day and night drive extremely fast winds. Because the orbit is so tight and the star is so close, the pressure gradients in the atmosphere are intense. Models for similar hot Jupiters suggest wind speeds in the thousands of kilometers per hour, thousands of miles per hour, easily supersonic in that gas. Those winds move heat from the dayside around the limb and across the night side. Hot gas flows over the terminator, cools slightly as it radiates energy away, then sinks, then returns in deep circulation cells. The result is brutal heat redistribution. The dayside stays incredibly hot, but the night side is dragged up to oven-level temperatures instead of dropping into deep cold. There is no place on this planet where you can talk about anything resembling a cool environment. Everything is either extreme or slightly less extreme. So you have a world where the day face is hotter than many small stars, and the night face is still hot enough to melt lead. With that much heat moving around, the obvious question is, what is the air actually made of, and why doesn't it cool itself down the way we expect from other hot gas giants? Normally, when Webb or other instruments look at a hot Jupiter, the spectrum shows clear fingerprints of certain molecules. You see water vapor, carbon monoxide, carbon dioxide, and often methane in cooler regions. These molecules don't just tell you about composition, they also act like thermostats. They absorb energy at some wavelengths and emit at others, helping the atmosphere radiate heat away into space in an efficient way. On this planet, Webb looks for those familiar patterns and mostly doesn't see them. The signatures of water vapor and carbon monoxide are extremely weak or missing. Instead, the spectrum is dominated by helium and unusual carbon-bearing molecules, things like chains and clusters of carbon atoms that show up when oxygen and nitrogen are largely absent. That means the atmosphere cannot use the standard set of coolant molecules to radiate heat in the usual way. Without those familiar coolants, the atmosphere behaves differently. Helium by itself is a poor radiator at these temperatures, and the exotic carbon molecules don't fill in the cooling role the way water or carbon monoxide would. Energy builds up more easily, and once gas heats to a few thousand degrees, it stays very hot unless there is a very efficient way to emit radiation. Here, the chemistry itself works against that. The air is more like a hot, carbon-rich plasma environment than a typical gas giant envelope. This is why the planet can maintain such extreme dayside and nightside temperatures. It's not just that it receives a lot of energy from the neutron star and from tidal heating. It's also that its atmosphere is not set up, chemically, to get rid of that energy in the most efficient way. The usual radiative balance is broken, and the climate locks into a very high temperature state. But how do we actually know the numbers for these temperatures? And how can you tell where the heat is on a world that, in a telescope, is just a single point of light smaller than a pixel? The trick is to use time, not just brightness. Webb watches this system continuously over at least one full 7.8-hour orbit. As the planet moves, different longitudes rotate into view. When the hot day side faces us, the total infrared brightness from the system goes up. When the cool night side faces us, it goes down. When the planet passes behind the neutron star from our line of sight, the planet's contribution disappears for a short time, creating a small dip in the light curve. By measuring these changes very precisely, astronomers build what's called a thermal phase curve, a record of how the planet's brightness changes with orbital phase. From the amplitude and shape of that curve, you can infer the day-night contrast and how efficiently the atmosphere moves heat around. A big contrast means poor heat redistribution. A smaller contrast means winds are doing a lot of work smoothing out the temperature. In this case, the numbers line up with a very hot day side, a still extremely hot night side, and strong atmospheric circulation. Webb then combines the phase curve with spectroscopy. It splits the infrared light into many narrow color bands and tracks how each one varies over the orbit. Some wavelengths probe higher layers in the atmosphere. Others see deeper down. That gives you a kind of crude 3D picture of how temperature and composition change with depth and longitude. For this planet, those data show the helium-carbon-dominated mix and the suppressed oxygen-bearing species we talked about. So, from a simple sequence of brightness measurements over less than 8 hours, you get a detailed view of a climate that is harsher than most stellar surfaces, with a day side at about 2038 degrees Celsius, a night side at about 649 degrees. Winds at thousands of kilometers per hour, and chemistry that refuses to cool the place down. But once you know the climate is this extreme, the next question is even more unsettling. What kind of formation history gives you an atmosphere dominated by helium and carbon with almost no oxygen or nitrogen? And what does that say about whether this is really a planet at all, or the stripped core of a dead star pretending to be one? How do you even get a planet that basically forgets two of the most important elements for normal planetary chemistry, oxygen and nitrogen, and still manages to have a thick, hot atmosphere? That's the point where PSR J2322-2650b stops being just extreme and starts looking like something that does not fit into the usual planet box at all. When Webb looks at the light from this planet and breaks it into a spectrum, the pattern that comes back is not the standard hot Jupiter signature. Instead of the usual mix of hydrogen with clear traces of water vapor and carbon monoxide, the atmosphere is dominated by helium and carbon. The hydrogen that you expect in large amounts is not the main story anymore. In that spectrum, you see strong signs of molecules made of carbon atoms linked together, things like C2 and C3, carbon pairs and carbon chains. These kinds of molecules only become prominent when oxygen and nitrogen are almost completely missing from the gas. If oxygen were around in normal amounts, it would grab carbon to make carbon monoxide or carbon dioxide. If nitrogen were around, you'd see other mixed species. The fact that you see pure carbon chains tells you, very directly, that the normal partners for carbon just are not there in any serious quantity. So right away, the atmosphere is telling you this is not the typical hydrogen plus a sprinkle of everything else gas giant. This is a helium-carbon envelope sitting at thousands of degrees wrapped around the planet mass object that lives 1,000,000 miles, about 1.6 million kilometers, from a neutron star. That's the chemical fingerprint of something that has been heavily processed, not a fresh planet that grew in a quiet disk. If helium and carbon are running the show, the obvious next question is, where did all the oxygen and nitrogen go? And why didn't they end up in the atmosphere the way they do on almost every other giant planet we've seen? In normal planetary chemistry, oxygen and nitrogen are hard to ignore. In a normal hot Jupiter that forms from a protoplanetary disk with roughly solar composition, you start with a lot of hydrogen, some helium, and smaller but still important amounts of oxygen, carbon, nitrogen, and other elements. As the planet cools and its atmosphere settles, carbon and oxygen link up to form carbon monoxide and, at lower temperatures, water vapor. Nitrogen shows up in molecules like ammonia or nitrogen gas. So, in a standard hot Jupiter, Webb and other telescopes see water vapor lines, carbon monoxide lines, sometimes carbon dioxide, and methane in cooler regions. These molecules dominate the infrared spectrum. Even if you heat the atmosphere and break some of them apart, their fingerprints don't just vanish. The element ratios are baked in from formation. On this planet, the spectra show almost none of that. The expected lines from water, carbon monoxide, and related molecules are extremely weak or effectively absent. Instead, you have carbon left to bond with itself, building those exotic chains and clusters, while helium sits in the background as the main filler gas. Oxygen and nitrogen are so scarce in the observable layers that they don't have a strong say in the chemistry anymore. Our current chemical and atmospheric models don't have an easy route to that state starting from normal planet-forming material. You don't just turn off oxygen and nitrogen in a gas giant without doing something very drastic. That's why this result is so unsettling. It forces you to consider histories that are much more violent than simple formation in a disk. If this planet were just a normal gas giant that formed far from its star and then migrated inward, what would you expect to see instead of this helium-carbon mix? You'd expect sizes and orbits that look extreme, sure, but the composition would still carry a memory of its birth environment. A standard hot Jupiter should show solar-like element ratios. Hydrogen and helium would dominate, but you would still clearly detect water vapor, carbon monoxide, maybe methane depending on temperature, and other common molecules. Even when we look at heavily irradiated hot Jupiters close to sun-like stars, that pattern holds. Temperatures can climb above 1,500 degrees Celsius, over 2,700 degrees Fahrenheit, and still the spectra show those molecules. They may be partially dissociated on the hottest dayside regions, but they reform on the night side, and you still see their signatures in the combined light. Here, that is not what Webb sees. Instead, the chemistry looks more like what you would expect if you took a star, peeled off its outer hydrogen-rich layers, and exposed deeper zones that have already gone through nuclear burning and lost a lot of their lighter elements. Those zones tend to be helium-rich and can be carbon-rich too, depending on how far into the interior you go. That's why some researchers looking at systems like this argue that calling this object a planet is more about convenience than about physics. Yes, it has a mass roughly similar to Jupiter, and yes, it orbits something we call a star. But if the material in its atmosphere is the same kind of stuff you normally find in a stellar core, and its origin is a stripped-down star, then it's not a planet in the same sense Jupiter is. It's a small stellar remnant that just happens to sit in the planet mass range. So if it doesn't behave like a normal hot Jupiter, and its chemistry looks more like a star's insides, what does that do to our formation models, the ones we use to explain most of the exoplanets on our lists? Those models assume planets form in protoplanetary disks, with a certain mix of elements and temperatures that change gradually with distance from the star. Gas giants pick up lots of hydrogen and helium, plus whatever heavier elements are in the local gas and dust. They can migrate inward, they can be scattered by other planets, but the basic bulk composition stays close to the original disk. You can tweak details, but you don't randomly end up with helium-carbon atmospheres almost completely missing oxygen and nitrogen. To get what we see here, you need either extreme post-formation processing or an exotic disk scenario we've never seriously considered. The first option is the stripped star scenario. You start with a normal companion star. The neutron star, through its wind and gravity, slowly removes mass from that star over millions to billions of years. You peel away the outer hydrogen-rich layers, then you start to dig into zones where helium and carbon dominate. Eventually, you're left with a compact core with roughly Jupiter's mass wrapped in an atmosphere that reflects that deeper composition, not disk gas. That's why some researchers looking at systems like this argue that calling this object a planet is more about convenience than about physics. Yes, it has a mass roughly similar to Jupiter, and yes, it orbits something we call a star, but if the material in its atmosphere is the same kind of stuff you normally find in a stellar core, and if its origin is a stripped-down star, then it's not a planet in the same sense Jupiter is. It's a small stellar remnant that just happens to sit in the planet mass range. So if it doesn't behave like a normal hot Jupiter, and its chemistry looks more like a star's insides, what does that do to our formation models, the ones we use to explain most of the exoplanets on our lists? Those models assume planets form in protoplanetary disks, with a certain mix of elements and temperatures that change gradually with distance from the star. Gas giants pick up lots of hydrogen and helium, plus whatever heavier elements are in the local gas and dust. They can migrate inward, they can be scattered by other planets, but the basic bulk composition stays close to the original disk. You can tweak details, but you don't randomly end up with helium-carbon atmospheres almost completely missing oxygen and nitrogen. To get what we see here, you need either extreme post-formation processing or an exotic disk scenario we've never seriously considered. The first option is the stripped star scenario. You start with a normal companion star. The neutron star, through its wind and gravity, slowly removes mass from that star over millions to billions of years. You peel away the outer hydrogen-rich layers, then you start to dig into zones where helium and carbon dominate. Eventually, you're left with a compact core with roughly Jupiter's mass wrapped in an atmosphere that reflects that deeper composition, not disk gas. The second option is to imagine a protoplanetary disk that is already highly processed, somehow depleted in oxygen and nitrogen, and enriched in helium and carbon in the region where this object formed. But that's hard to arrange. You'd need a very specific sequence of events that removes certain elements and not others, and you'd have to do it while still leaving enough mass to build a Jupiter-sized object. Right now, there is no standard path in disk chemistry that does that cleanly. This is why this planet is so disturbing to theorists. Neither path is fully comfortable. The stripped star scenario explains the chemistry and the extreme orbit better, but it has its own problems, like how the object survives the supernova and the long ablation phase. The exotic disk scenario would let you keep calling it a planet in the traditional sense, but it doesn't match what we know about how disks behave around newborn stars. In other words, the spectrum of this single world is telling you that your simple categories are not enough. You can't just say Jupiter mass plus close orbit equals hot Jupiter, case closed. You have to ask where the material came from, how it was processed, and whether you're actually looking at a former star that has been demoted into the planet mass range by a neutron star companion. And once you accept that the air above those clouds is full of helium and carbon with almost no oxygen or nitrogen, the next step is to ask, what does that do to the actual weather on this world? And what kind of strange solids and liquids form when a carbon-rich atmosphere at thousands of degrees is squeezed under enormous pressure deep inside the planet? How bad does the weather have to get before you stop calling it weather and start calling it a chemical reactor wrapped around a planet? That's basically what's going on in the atmosphere of this planet PSR J2322-2650b. Once you have a helium-carbon atmosphere with almost no oxygen or nitrogen and temperatures of thousands of degrees, the next step is that the air itself starts turning into soot and crystal under insane pressure and heat. Webb's spectra don't just show gas, they also suggest the presence of solid or liquid particles suspended in the upper atmosphere, and the best match for those is carbon-based haze, basically soot. The carbon chains like C2 and C3 that show up in the spectrum don't just stay as clean molecules forever. Under the right temperature and pressure conditions, some of that carbon condenses out into tiny particles. So instead of clouds made of water vapor like on Earth, or ammonia and water like on Jupiter and Saturn, this planet has clouds made of carbon-rich haze, dark, sticky particles that absorb light very efficiently. You're dealing with an upper atmosphere that's more like a permanent smog layer than anything you'd call a bright, reflective cloud deck. In visible and ultraviolet light, those particles would make the planet look very dark and muted. In infrared, they re-radiate the absorbed energy as heat, contributing to the extreme temperatures you already see. The key point is simple. The carbon that oxygen and nitrogen would normally lock into familiar molecules is instead free to condense into solid grains. Those grains float, clump, and settle just like dust and smoke do in an atmosphere. This changes how light moves through the air, how heat is trapped, and how energy moves from the deep interior out to space. If the upper atmosphere is full of soot-like particles, what happens deeper down, where the pressure and temperature climb far beyond the levels we can reproduce easily in labs on Earth? As you go deeper into this planet, pressure rises very quickly. A Jupiter-mass object already reaches millions of times Earth's surface pressure in its interior. Now add the extra gravitational squeeze from being stretched into that lemon shape, plus the tidal heating and the general high-energy environment, and you'd have a place where carbon is being pushed into some of its most compact and stable forms. On Uranus and Neptune, models suggest that deep inside, carbon from methane could form diamond rain. Carbon atoms link together into crystal structures under high pressure, forming diamond, which then sinks toward the core. Here, the conditions are even more extreme. The atmosphere is richer in carbon, and the pressures at depth are at least as high, if not higher. So in this planet, it's very likely that at certain depths, carbon transitions from gaseous and soot-like forms into liquid or solid diamond. You'd have regions where diamond crystals form, grow, and then sink deeper, maybe melting into a super dense carbon layer. You can think of it as a kind of carbon cycle, but instead of trees and carbon dioxide, it's gas, soot, and diamond, all driven by gravity and heat. We can't drill into this planet, but this picture comes out of combining what we know from high-pressure physics, from ice giants in our own system, and from the helium-carbon composition that Webb sees. The logic is straightforward. Lots of carbon, enormous pressure, very high temperature, and enough time, and diamond formation becomes not just possible, but likely. So in this planet, it's very likely that at certain depths, carbon transitions from gaseous and soot-like forms into liquid or solid diamond. You have regions where diamond crystals form, grow, and then sink deeper, maybe melting into a super dense carbon layer. You can think of it as a kind of carbon cycle, but instead of trees and carbon dioxide, it's gas, soot, and diamond, all driven by gravity and heat. We can't drill into this planet, but this picture comes out of combining what we know from high-pressure physics, from ice giants in our own system, and from the helium-carbon composition that Webb sees. The logic is straightforward. Lots of carbon, enormous pressure, very high temperature, and enough time, and diamond formation becomes not just possible, but likely. So you have soot higher up and potential diamond phases deeper down. That leads to the next question. How does all this carbon actually move? Is it just sitting there, or is it being churned constantly by the insane energy flows in this system? The answer is that nothing here is calm. The soot clouds in the upper atmosphere are sitting in a zone where they are being hit from above by high-energy particles and radiation from the neutron star, and heated from below by tidal energy and internal heat. That combination is perfect for driving violent convection. Here's the cycle. Gas in the deep atmosphere heats up, becomes buoyant, and rises. As it rises, the surrounding pressure drops and the gas expands and cools. Some of the carbon in that gas condenses into tiny particles, forming soot or haze. Those particles can clump together into larger grains. As they grow or as they move into regions where the air is denser, gravity pulls them back down. They sink, possibly evaporate again at deeper, hotter layers, and the cycle repeats. This is a planetary-scale carbon engine. Simple carbon-bearing molecules are turned into complex clusters and grains, transported upward and downward, broken apart by radiation, and rebuilt under pressure. You're constantly feeding energy into the system from both sides, above and below. That's a recipe for chemistry that goes way beyond the tidy reactions we model in simple hot Jupiter atmospheres. You can get long-chain carbon molecules, ring structures, and maybe even more exotic phases in intermediate layers. On top of that, the winds we talked about earlier, likely moving at thousands of kilometers per hour, are shearing and mixing this whole system horizontally. Hot, soot-loaded air from the dayside is dragged toward the night side, while slightly cooler gas returns at other levels. Vertically, convection is lifting and sinking material. The result is a three-dimensional, constantly shifting lattice of carbon chemistry, not just a single uniform layer. So why should you, sitting safely on Earth, care whether this far-off planet has haze made of soot and deep layers that might rain diamond? It matters because these particles control how the planet interacts with radiation, and that directly affects how we interpret data from this world and from every other extreme exoplanet we've studied. Dark soot in the upper atmosphere absorbs incoming energy very efficiently. Instead of reflecting light back to space, it turns a lot of that energy into heat. That can create strong temperature inversions, layers where the temperature increases with altitude instead of decreasing, and it can shift where in the atmosphere most of the heat is stored. Diamonds, deeper down, have very different optical properties. They are transparent at some wavelengths and reflective at others, and under high pressure, they can form strange phases that affect how heat moves through the interior. Our radiative transfer models, the mathematical tools we use to go from observed spectra to temperature and composition profiles, usually assume simpler cloud structures: silicate dust, metal oxides, maybe some hydrocarbon haze. A planet with thick soot and potential deep diamond layers forces us to stress test those models. If we can't match what we see from this planet with our current tools, that means we might be misinterpreting the data from other planets that look more normal at first glance. In other words, this planet isn't just weird for its own sake. It's a calibration point at the edge of what's possible. If your physics can handle a helium-carbon atmosphere, soot clouds, and diamond rain under the glare of a neutron star, then you can trust it more when you apply it to regular hot Jupiters and warm Neptunes. If your models fail here, you have to go back and adjust them, and that change will ripple out to how you think about dozens or hundreds of other exoplanets. So now you have a full stack: a helium-carbon atmosphere, soot haze in the sky, likely diamond formation deep inside, and a constant input of energy that keeps the whole system churning. The air itself is being built and rebuilt in a loop of extreme physics and chemistry. The next step is to look at how this entire atmosphere behaves as a single system over time. Because in this environment, it's not just that the weather is violent, it's that the atmosphere can actually start working against the planet that holds it, rotating in strange directions, getting stripped by the pulsar wind, and acting as the interface between a neutron star's magnetosphere and the barely surviving world. How do you even talk about normal weather when the whole upper atmosphere might be rotating backwards compared to the planet itself? That's one of the strangest hints coming out of the Webb data for this planet. It's not just hot, not just distorted. The air up high doesn't seem to be playing by the same rules as the body underneath. When astronomers look at how the planet's brightness changes over its 7.8-hour orbit, they don't just get day versus night. They can also see where the hottest region sits on the dayside. On many hot Jupiters, the hottest point is shifted a bit east of the substellar point because winds blow heat in the same direction as the planet's rotation. Here, the best fit to the data hints that the hot spot may be shifted the other way, toward the west. If that's true, it means the jet streams in the upper atmosphere are moving retrograde, opposite the direction the planet spins. In other words, the planet's body rotates one way, and the high-altitude winds at the top of the atmosphere race around the other way. That's not how we think about typical gas giant dynamics. On Jupiter and Saturn, and on most hot Jupiters we studied, the main jets generally follow the direction of rotation. So what could flip an atmosphere like that? The forcing here is extreme and very one-sided. One hemisphere is locked under constant heating from the neutron star and from tidal energy. The other sits in permanent night, but still burns at over 1,000 degrees Fahrenheit. The radiation pattern from a pulsar isn't a smooth, steady glow, it's beamed and pulsed. All of that can set up pressure gradients and torque on the atmosphere that don't match the underlying spin. On top of that, the neutron star's magnetic field and the charged particle wind may dump momentum into the upper layers in a preferred direction. In simple terms, the top of the atmosphere is being yanked around more by the star's radiation and particle flow than by the planet's own rotation. The result is an upper layer that, at least in part, runs counter to the bulk spin, a backwards atmosphere wrapped around a tidally locked lemon-shaped world. Once you accept that the flow can even flip direction, the next obvious question is, just how fast is this air actually moving when you have such insane day-night contrasts and such a tight orbit? You've got a temperature difference of roughly 1,400 degrees Celsius, something like 2,500 degrees Fahrenheit, between the hottest dayside regions and the coolest nightside regions. You've also got an orbit that completes in less than 8 hours at a distance of about 1.6 million kilometers, roughly 1 million miles. That combination is perfect for driving extremely strong winds. Hot gas on the dayside expands and rises. Cooler gas on the night side contracts and sinks. The pressure difference between those regions pushes air from high pressure zones to low pressure zones. Because the planet is spinning and tidally locked, those flows get twisted into jet streams. On Earth, that setup gives you jet streams with speeds of a few hundred kilometers per hour at most, a few hundred miles per hour in extreme storms. On this planet, the same physics plays out, but with much higher energy. Models for similar ultra-hot Jupiters suggest wind speeds that can easily reach several thousand kilometers per hour, several thousand miles per hour. That's supersonic flow in the local gas, fast enough that shock waves can form where air masses collide. Those winds do two big things. First, they redistribute heat, dragging some of the dayside energy over the limb and across the night side, which is why the dark hemisphere is still oven-level hot instead of freezing. Second, they churn chemicals around the globe, spreading those carbon-based molecules and soot particles, mixing the upper atmosphere horizontally and vertically. Now, put that together with the backwards flow hint. You may have a situation where deeper layers track the planet's rotation, while higher layers are driven the other way by pulsar irradiation and magnetic forces. At the boundaries between those layers, you get strong wind shear, with air sliding past air at huge relative speeds. That's a perfect setup for turbulence, wave breaking, and additional heating. With that much motion and that much radiation, you'd expect the atmosphere to get peeled away over time. So the next question is, why does this planet still have anything left to call an atmosphere at all, instead of just a bare, stripped core? Under normal circumstances, intense irradiation plus fast winds equals atmospheric escape. High-energy photons and charged particles hit the upper atmosphere, ionize atoms, and heat the gas until it reaches escape speeds. The strongest winds and the weakest bound regions let gas flow outward along magnetic field lines, leaking mass into space. Over millions to billions of years, that process can seriously thin or even remove an atmosphere. Here, the pulsar wind is a constant source of erosion. High-energy particles slam into the dayside, especially around the magnetic poles. The upper atmosphere gets ionized and heated. Some fraction of that gas will be driven off into space, forming a kind of comet-like tail or an extended cloud. Wind shear and turbulence can help mix fresh material upward, where it can also be stripped. But you probably have a different internal structure than a normal gas giant. If it really is the remnant core of a larger star, its deeper layers are rich in helium and carbon, not just hydrogen. As the outer atmosphere is peeled away, those inner layers can expand and feed new material into the envelope. So even while the pulsar wind is eroding the atmosphere, the planet itself is resupplying it from below. That sets up a long-term battle. On one side, you have erosion by radiation, particle winds, and supersonic shearing flows that help gas escape. On the other, you have internal reservoirs of helium and carbon that can replenish the outer layers as mass is lost. If the stripping rate is too high, the planet will keep shrinking and eventually be destroyed. If the resupply is strong enough, it can hang on for billions of years in a kind of metastable state, always losing, always replacing, but never completely disappearing. So the atmosphere isn't just a passive blanket of gas, it's the front line in a fight between the neutron star and the remnant core. That leads to one more level of complexity, because in a system like this, the atmosphere isn't just dealing with radiation and gravity, it's sitting right where the pulsar's magnetic field and the planet's plasma environment crash into each other. You can think of this planet as sitting at the inner edge of the pulsar's magnetosphere, the region where the neutron star's magnetic field dominates the motion of charged particles. The planet's atmosphere, especially the ionized upper layers, becomes a target for those particles. As they slam in, they can drive currents along magnetic field lines, just like auroral currents near Earth's poles, but far more intense. On Earth, charged particles from the sun hit our atmosphere and create auroras, and they can induce currents in power lines and pipelines. At Jupiter, interactions between the planet and its moon Io generate powerful radio emissions and bright auroral hotspots. Scale that idea up to a neutron star and a carbon-rich, ultra-hot atmosphere, and you get something much more extreme. In this system, charged particles hitting the atmosphere could set up huge electrical currents, heating specific regions, changing local chemistry, and possibly creating radio signals tied to the planet's orbit. The atmosphere becomes a conducting layer where the pulsar's magnetic energy is partially dissipated. It's less like a quiet shell of gas and more like a live electrode plugged into a cosmic particle accelerator. That interface controls how much energy gets deposited where, how fast the atmosphere is stripped, and how the winds respond. It might even feed back on the pulsar's local magnetosphere in subtle ways, adding small modulations to the pulses we see. For now, those details are mostly theoretical, but the basic picture is clear. This planet's atmosphere is not just along for the ride, it's actively interacting with one of the most hostile environments in the universe. So step back and stack everything you've heard so far. You have a lemon-shaped Jupiter mass remnant orbiting a neutron star in 7.8 hours with a helium-carbon atmosphere, soot clouds, possible diamond rain, backwards high-altitude winds, and a constant battle between erosion from above and resupply from below, all wired into a pulsar's magnetic field. The natural next question is, how did we even figure all of this out from a system that, in a telescope, is just a faint point of light 750 light-years away? How did Webb turn a tiny infrared signal into this detailed physical picture of a planet being slowly destroyed? Most of the time, the hardest part of studying an exoplanet is that the star completely drowns it out. A normal sun-like star is so bright in visible and infrared light that the planet's signal is just a tiny ripple on top of a huge glare. With this system, that problem flips, and that flip is exactly why this planet is even visible to James Webb Space Telescope in the first place. Normally, a telescope has to fight the star. You're trying to pick up a little bit of extra infrared light when the planet's hot dayside comes into view, or a tiny dip when it passes in front of the star. Here, the host is a pulsar, which pumps almost all of its power into radio waves, X-rays, and gamma rays. Those are bands Webb barely touches. In the infrared, the pulsar is relatively faint, almost like a weak background light. This planet, though, is a different story. At over 2,000 degrees Celsius on the dayside, around 3,700 degrees Fahrenheit, it glows hard in infrared. So when Webb points its mirrors at this system, it doesn't get blinded by the star and struggle to see the planet. It gets a relatively clean view of a very hot object against the dim infrared background. For once, the atmosphere signal doesn't have to be dug out of heavy starlight. It's right there in the data. That unusual setup is the first big advantage. The second advantage comes from the fact that this planet races around its neutron star in just 7.8 hours, which means you can watch an entire orbit in a single observing session. The way Webb really pulls information out of this is by sitting on the system and recording how the total infrared brightness changes over that full orbit. When the hot day side rotates into view, pointed more toward us, the system looks brighter in infrared. As the planet continues around and the cooler night side faces us, the total infrared signal drops. When the planet swings behind the pulsar from our point of view, its contribution briefly disappears entirely, leaving only the background from the neutron star and any surrounding material. If you plot that brightness against time, you get a smooth, repeating curve. That curve is called a thermal phase curve. The high point on the curve corresponds to when the hottest part of the day side is in view. The low point corresponds to when we're mostly seeing the night side. The depth of the little dip when the planet goes behind the pulsar tells you exactly how much infrared light was coming from the planet alone. By fitting that curve with models, astronomers can estimate the dayside temperature, the night-side temperature, and how efficiently heat is being shifted around by winds. For this planet, that fit gives you a dayside around 2,038 degrees Celsius and a nightside around 649 degrees, or about 3,700 and 1,200 degrees Fahrenheit. It also tells you that the atmosphere has to be moving heat aggressively, because the night is still incredibly hot rather than freezing out. But brightness alone only tells you how hot different sides are. To figure out what the atmosphere is actually made of, Webb has to split that light into a spectrum and read it like a barcode. Webb does this with its infrared spectrographs. Instead of just measuring how bright the planet is, they spread out the light into many narrow wavelength bins. Each molecule in the atmosphere absorbs and emits light at specific wavelengths, like a set of sharp spikes and dips in the spectrum. Water vapor has its pattern. Methane has its pattern. Carbon monoxide and carbon dioxide each have their own. When astronomers looked at this planet's spectrum, they didn't see the usual strong features from water, carbon monoxide, or methane that show up on most hot Jupiters. Instead, the lines that stood out were from helium and from exotic carbon species, including those C2 and C3 molecules you heard about earlier. The spectrum is skewed toward helium and carbon, with oxygen-bearing and nitrogen-bearing molecules heavily suppressed or missing. That mix matches the idea of a helium-carbon atmosphere and backs up the picture that this planet has an unusual composition, not just a normal composition pushed to high temperatures. If it were simply a very hot version of a standard hot Jupiter, you might be able to explain some missing molecules as being broken up by heat, but you wouldn't get rid of the elemental oxygen and nitrogen so completely. The fact that their molecular fingerprints are mostly gone tells you the bulk chemistry is different. Webb doesn't stop at a single spectrum either. It can watch how the spectrum changes throughout the 7.8-hour orbit. At some wavelengths, you're more sensitive to higher altitudes. At others, you see deeper into the atmosphere. By tracking how each wavelength brightens and dims over time, you can map not just a single temperature number, but how temperature and composition vary with longitude and depth. In this system, that time-dependent spectroscopy is what lets astronomers pick up hints like a possible westward shift of the hotspot, which suggests backwards retrograde winds at high altitude. It also helps separate the contributions of clear gas and soot haze, because those affect different parts of the spectrum in different ways. All of that together, clean infrared background, fast orbit, strong planet signal, and high-resolution spectroscopy turns what would normally be a barely detectable dot into a detailed physical object in our models, with mapped temperatures, winds, and chemistry. And the key is that the host star is a pulsar, not a normal bright infrared source. The thing that makes this system look hostile for life is exactly what makes it ideal for this kind of observation. So this flips the way we think about where to point Webb and future telescopes. For a long time, pulsar planets were treated as oddities, more like fun facts than as serious atmospheric targets. The thinking was that if anything survives there, it's probably just a bare rock or a weird remnant. This planet shows that's not the full story. In the infrared, a faint central object plus a very hot companion can actually be easier to analyze than a normal star-planet pair. If you can do this for a world orbiting a neutron star in 7.8 hours, you can try similar tricks on other extreme systems. White dwarf planets, low-mass companions around compact objects, or planet mass remnants in tight post-supernova binaries suddenly become interesting targets, not just curiosities. Anywhere the central object is dim and infrared, but violent and high energy bands, you have a chance to read the planet's atmosphere more cleanly than around a normal sun-like star. So this system doesn't just add one bizarre object to the catalog, it opens a new hunting ground. It says, don't ignore the planets around dead stars. In infrared, they might be the easiest ones to read in detail. And once you realize you can read them this well, the next step is to ask the big origin question head-on. If the chemistry looks like a stellar core, the orbit is right on the edge of the Roche limit, and the host star is a millisecond pulsar, what formation story actually fits all of that? Are you really looking at a planet, or are you looking at the stripped-down corpse of a former star, slowed and carved until it happens to weigh about as much as Jupiter? How do you get from a normal star to something the size of Jupiter without blowing it to dust? That's the key origin question here. And the most serious answer on the table right now is that this planet started life as a star and was slowly carved down by its neutron star companion over incredible spans of time. Astronomers have a name for systems that do this: black widow pulsars. In those systems, a neutron star orbits with a low-mass companion. The pulsar throws out a constant wind of high-energy particles and radiation. That wind slams into the companion star and gradually strips material off its surface. Over millions to billions of years, the companion loses mass, shrinking from something like a normal sun-like star down to a very low-mass remnant. PSR J2322-2650 is suspected to be in that black widow category, because the object we're calling a planet has only about 10 to the minus 3 solar masses, which is roughly 1 Jupiter mass. In other words, the companion here is in the mass range we usually reserve for gas giants, not stars. But the environment and the chemistry don't match a normal planet story. They match something that has already been through a full stellar life cycle and then a long erosion phase. In the Black Widow picture, you start with a neutron star and a real star in a close binary orbit. The neutron star accretes some material from the companion, spins up to become a millisecond pulsar, and its particle wind intensifies. That wind, plus tidal effects and radiation, strips gas off the companion's outer layers. The mass flows away, some falls toward the neutron star, some is ejected from the system. Over time, the companion gets lighter and lighter. Its outer hydrogen-rich envelope is peeled off. That leads directly into the next piece of the puzzle. If you keep peeling a star like that, layer after layer, what do you eventually expose? And does that match what Webb is seeing in the atmosphere of this planet? Inside a star, nuclear fusion changes the composition as you go deeper. The outer layers are rich in hydrogen, like the sun's surface. Deeper inside, after long periods of burning, you get zones dominated by helium, then regions where helium burning has produced carbon and oxygen, and so on. In lower mass stars, you may never reach the heavier elements in a big way, but you still build up helium and carbon-rich regions in the interior. If the neutron star strips away enough of the outer hydrogen and some of the helium, you can end up with an exposed core region that is helium and carbon dominated, with much lower amounts of oxygen and nitrogen in the outer layers. That is exactly the sort of composition Webb is hinting at when it sees a helium-carbon atmosphere with strong carbon chain molecules and very weak signatures of water, carbon monoxide, and nitrogen-based species. So in this scenario, this planet is not a planet in the traditional sense. It is the surviving core of a former star, demoted down to planet mass. The atmosphere you see is the outer skin of that core, not a gas giant envelope built from a protoplanetary disk. You're basically orbiting a stellar corpse that has been shaved down to roughly Jupiter's mass, mapped by Webb as if it were a normal exoplanet. This fits the mass and the basic composition picture surprisingly well, but it still leaves some uncomfortable gaps. If this is the remnant core of a shredded star, why doesn't the chemistry match our stellar core models perfectly? And how did the system avoid completely destroying the companion during both the supernova and the long erosion phase? First problem: chemistry. Our models of stellar interiors say that in certain mass ranges, you should end up with particular ratios of helium, carbon, oxygen, and other elements in the core. The atmosphere of this planet has a lot of helium and carbon, and seems to be very poor in oxygen and nitrogen. That's suggestive, but the exact ratios you infer from the spectra do not line up perfectly with any single clean layer from a standard stellar evolution model. That can mean a few things. It might mean that we're seeing a mix of layers, not a pure slice, because convective mixing and pulsar-driven stripping have stirred things together. It might mean that the long period of mass loss changed the composition profile in ways our current models don't track correctly. Or it might mean that our models for how stars behave under this kind of constant ablation are still too simple. Second problem: survival. This object had to live through at least two brutal phases. First, the original star exploded as a supernova to create the neutron star. Any companion in a close orbit during that event is under serious threat of being blasted apart or ejected from the system by the sudden loss of mass and the shockwave. Somehow, this companion stayed bound and didn't get fully destroyed. Then comes the long black widow phase, where the pulsar's particle wind and radiation strip material from the companion over millions to billions of years. If the stripping rate is too high, the companion vanishes entirely, leaving only the neutron star. If it's too low, you don't peel deep enough to reach the helium-carbon-rich layers you see now. This system seems to have landed in a narrow zone where the stripping has been strong enough to sculpt a stellar core, but not strong enough to erase it completely. That balance is tricky. It doesn't come out naturally in every model we run. So even with the Black Widow idea, you're still looking at a fine-tuned history. The supernova had to leave the binary intact. The spin-up and mass loss had to happen in just the right way. The current pulsar wind has to be energetic enough to keep ablation going, but not so strong that the companion is already gone. The chemistry we see suggests that the companion has been peeled down to deep layers, but the exact profile isn't a clean match to any one theoretical prediction. Because of all that, theorists are starting to treat this object as something that deserves its own label, not just a weird planet, and not just a stripped star. The term that makes sense here is something like a pulsar planet core. In that picture, this planet represents a new class of objects, remnants of stars that have been carved down by pulsar winds and tidal stripping until they sit in the planet mass range. They are not brown dwarfs, which are failed stars that never ignited full hydrogen fusion. They aren't regular planets, which form in disks around young stars. They're something in between, an end product of extreme binary evolution. The key differences are origin and composition. A normal gas giant like Jupiter forms out of a cold, dusty disk, picks up a huge hydrogen-helium envelope, and keeps a mix of heavier elements that reflect the original disk composition. A pulsar planet core like this one starts as a star, runs nuclear reactions in its interior, then gets stripped slowly until its innermost layers remain. The mass might be similar, around 1 Jupiter, but the chemistry and structure are totally different. Once you admit this category exists, you have to ask how many of the planets around compact objects might actually be these stellar remnants. And you have to decide where to draw the line in your catalogs. Do you list this as a planet, a stellar remnant, or both? On a mass radius plot, it sits in the planet zone. On an origin diagram, it sits firmly in the processed star zone. That's why this object is so important. It's not just another exotic world. It's a live test case for how we label things. If you can have planet mass objects that are really half-eaten stars, then the word planet is no longer about mass alone. It has to include history and chemistry. And once you start framing it that way, you bump straight into the next big question that this system forces on you. If something has the mass and orbit of a planet, but the guts and past life of a star, does it even make sense to keep calling it a planet? Or are we overdue for a complete rewrite of what that word means in extreme systems like this? How many rules does something have to break before you stop pretending it fits the old label? That's the problem with PSR J2322-2650b. And yeah, I'll use the name once and then just call it this planet. On paper, it checks the simple boxes you've been using for years. It has roughly Jupiter's mass and it orbits a star. By the most basic observational definition, that makes it a planet. But as soon as you look at where it came from, what it's made of, and where it lives, it stops behaving like anything that word was invented for. It's the same kind of problem Pluto gave us, except now, instead of arguing about icy rocks at the edge of the solar system, you're arguing about a Jupiter mass helium-carbon core being roasted next to a neutron star. The way exoplanet catalogs work right now is pretty blunt. You measure a mass, or a radius, or both. You measure an orbit. If the mass is below a certain threshold and it orbits something you call a star, it goes in the planet column. That's it. Those catalogs don't track the full origin story. They don't ask whether the object formed in a protoplanetary disk, or whether it's a leftover core, or whether it's the burned-out husk of a star. They just log what they can measure cleanly: how heavy it is, how big it is, and how it moves. This worked fine when all your examples were relatively normal. A Jupiter mass object at a few tenths of an astronomical unit from a sun-like star, okay, hot Jupiter. A rocky object in a short orbit around a red dwarf, super-Earth or sub-Neptune. Even the weird stuff still sort of fit. But this planet doesn't just stretch that approach. It exposes the main weakness. Mass and orbit don't tell you anything about history, and history matters. If this planet really started life as a normal star, then went through a supernova from its companion, then got stripped for hundreds of millions or billions of years by a pulsar wind until only a helium-carbon core was left, what do you call it? By origin, it's a stellar remnant. By mass, it's a planet. By environment, it's sitting in a regime you usually treat as uninhabitable and hostile, even for gas giants. That's 3 different axes giving you 3 different answers. You can try to say, okay, we'll just stick with the observational definition. If it orbits a star and has about a Jupiter mass, it's a planet. But as soon as you do that, you're hiding the most important part of the story. You're pretending that this planet and Jupiter belong to the same family, when one formed quietly out of a disk 5.2 astronomical units from the sun, and the other is the peeled, roasted core of a former star clinging to life at about 0.010 astronomical units, roughly 1.6 million kilometers, about 1 million miles, about a neutron star. So you either keep the label and accept that planet now covers wildly different beasts, or you tighten the definition and admit that some of the things you've been calling planets are something else. This is exactly what happened with Pluto. Once you discovered a whole population of similar objects, the old definition snapped. Here, you're discovering that planet, based only on mass and orbit, is too crude for the weird cases. That pushes you toward a different way of classifying things. Instead of just asking how heavy is it and what does it orbit, you have to ask 2 more questions. What is it made of, and how did it get that way? Composition is the obvious new axis. Jupiter mass does not automatically mean Jupiter-like anymore. If you look only at a light curve from far away, this planet might show up as a regular short-period hot Jupiter. Big transit depth, tight orbit, strong infrared signal. But as soon as you split the light and read the spectrum, you see helium and exotic carbon species and almost no oxygen-bearing molecules. Jupiter has hydrogen and helium with traces of water, methane, ammonia, and other familiar stuff. This planet's air looks like a stripped stellar interior. That difference in composition is not a detail. It tells you the bulk material came from deep inside a star, not from a cold protoplanetary disk. And that leads straight to the second new axis: history. If you want your categories to actually mean something, you have to care about formation channels. A classical planet is born in a disk around a young star, building up from dust and ice grains to rocks, then to cores, then grabbing gas if it grows fast enough. A brown dwarf is something that formed more like a star by direct collapse of a gas fragment, but didn't get massive enough to sustain full hydrogen fusion. A white dwarf is the leftover core of a sun-like star. This planet doesn't fit any of those cleanly if you only look at mass, but if you step back and look at how it likely formed, it fits naturally into the stripped star track. Star forms, star orbits another star, one explodes into a neutron star, the neutron star's wind and gravity carve down the companion until only a planet mass core is left. The fact that the end product weighs about as much as Jupiter is almost an accident. The process that made it is totally different from the one that made Jupiter. So what do you do with your categories once you've seen an object like this? Do you create a new label like pulsar planet core and split the planet mass objects into subgroups based on origin and composition? Do you mark some catalog entries as planet and others as remnant planet mass? Whatever you choose, you can't unsee the fact that a single number, one Jupiter mass, hides two completely different stories. And this planet doesn't just cause trouble on its own. Once you accept that objects like this exist, you have to go back and ask hard questions about other borderline cases. Which planets around white dwarfs and neutron stars are really leftover stellar cores? Which objects near the brown dwarf mass boundary are failed stars? And which are overgrown planets that accreted too much gas in a disk? Where exactly do you draw the lines between planet, brown dwarf, and low-mass star when history and chemistry don't line up neatly with mass? That's the bigger taxonomy shock this one system forces. You might end up redrawing the map for thousands of entries. Some things you've been calling planets will probably get relabeled as remnants. Some brown dwarfs might be more planet-like than star-like in how they formed. The simple boxes on your diagrams, planet here, brown dwarf there, star over there, start to look more like a continuous field with overlapping regions. This planet is small in the cosmic sense, roughly Jupiter's size, but the impact on how you name things is huge. It shows that the universe doesn't care about your clean categories. It will happily put a star through a shredder, leave a core weighing about 0.001 times the sun, and park it in an orbit where you're tempted to slap the planet label on it. Then, when you look closer, it forces you to admit that your labels are just approximations, and sometimes they're wrong. And once you start thinking this way, there's an even sharper question waiting for you. If this object is so close to the edge between planet and stellar remnant, and it lives in such a violent place, why hasn't that edge been crossed already? With a pulsar blasting it, with tides stretching it, with winds trying to blow its atmosphere away, how is there still anything left to argue about at all? Why hasn't this planet been completely destroyed? How weak does a neutron star have to be, and how strange does the setup have to get for a planet to sit 1 million miles away and not be turned into pure debris? That's basically the survival story for PSR J2322-2650b, and from now on, I'll just call it this planet. The only reason there's anything left to talk about is that the pulsar it orbits is, by millisecond pulsar standards, weirdly gentle. Back when the system was first studied in detail, Spiewak and colleagues pointed out that PSR J2322-2650 has a very low spin-down luminosity for a millisecond pulsar. In simple terms, spin-down power is the energy the neutron star is losing as it slowly slows its rotation. A rapidly spinning pulsar with a strong magnetic field can dump a huge amount of energy into its surroundings through radiation and a particle wind. Here, that power output appears to be on the low side, still extreme by your standards, but low compared to more violent cousins. That matters because the spin-down power feeds the pulsar wind, the constant stream of high-energy particles flying out along magnetic field lines. If that wind is too strong at the distance of this planet, anything in its path gets stripped quickly. Gas is ionized, heated, and driven off. Over relatively short timescales, the companion would just vanish. The fact that we still see a Jupiter-mass object in a 7.8-hour orbit tells you that for billions of years, the pulsar has been blowing hard enough to erode a star, but not so hard that it completely erases it. So the first part of the answer to why is this planet still here is that the central engine is oddly mild for what it is. PSR J2322-2650 is still dangerous, but its output is low enough that a companion can survive for very long periods without being fully ablated. If you swapped it for a more energetic pulsar with higher spin-down power, there probably wouldn't be anything left in this orbit at all. The next piece is the erosion rate itself. If the pulsar is chipping away at this planet, how fast is it doing it? And why hasn't that process finished the job yet? Rough estimates put the mass loss rate from the companion at around 10 to the 13th grams per second. That sounds ridiculous at human scales, about 10 million tons of material blown off every second. But you have to compare it to the total mass. This planet has about Jupiter's mass, on the order of 2 times 10 to the 30th grams. At 10 to the 13th grams per second over a billion years, you remove about 3 times 10 to the 29th grams, which is a large amount, but still only a fraction of the total mass. So the pulsar wind has been eating away at this planet for a very long time, but not at a rate that guarantees complete destruction within the current age of the system. Instead, it's more like a slow cooking process. Over time, you peel away the outer layers, exposing deeper and deeper material without ever fully erasing the core. Too much power and you blow the whole thing apart or strip it down to nothing very quickly. Too little power and you barely touch the outer layers. You never get to the helium-carbon-rich zones Webb is now seeing. This planet appears to sit in a narrow band between those extremes. The erosion has been strong enough to change its composition at the surface, but not strong enough to erase it. That's why the planet we see today looks like a helium-carbon core, not a typical gas giant and not a bare rock. There's another twist that helps it hang on, and it comes from the fact that the planet is tidally locked. That detail isn't just about day and night, it also changes how the erosion is applied. Being tidally locked means one hemisphere always faces the pulsar. That side takes the full force of the radiation and the particle wind. It's the permanent dayside, the one at over 2,000 degrees Celsius, where the high-energy assault is most focused. The night side, permanently turned away, still gets hot through circulation, but it doesn't take the direct hit of particles and high-energy photons in the same way. You can think of the dayside as a sacrificial face. It's where ionization, heating, and atmospheric escape are strongest. Gas is stripped away there, flows outward, and some fraction achieves escape velocity. Meanwhile, the night side acts as a partial reservoir. Atmospheric circulation, driven by the huge temperature difference and by the planet's rotation, constantly moves material from the night side to the day side and back again. This way, some of the mass that would otherwise be permanently locked on the safe side still cycles around and gets exposed, but not all of it at once. That spreads out the erosion over both hemispheres and buys time. The planet loses mass steadily, but at any one moment, a lot of material is on the far side, shielded from the worst of the pulsar wind. It's not protection in the sense of making the place safe, it's more like slowing the rate at which the whole atmosphere is fed into the furnace. On top of that, because this planet is likely the remnant core of a former star, its interior has deep layers of helium and carbon. As the outer atmosphere is stripped, those inner layers can expand and refill the envelope. So even as the day side loses gas to the pulsar wind, the planet itself can resupply some of what was removed, pushing fresh helium-carbon-rich material upward. That resupply keeps the atmosphere from collapsing completely, even as mass is steadily lost. Put all these pieces together, and you get a picture that's very far from a stable, comfortable system. This planet is not safe. It's just not dead yet. It sits in a metastable state, balanced on a knife edge between survival and total ablation. If the pulsar spin-down rate changes over time, its power output changes. If the magnetic field evolves, the shape and strength of the pulsar wind change. If the orbit shrinks a little more because of tidal interactions, the planet moves closer to the Roche limit, where tidal forces can finally tear it apart. Small shifts in any of those parameters can push the system toward a tipping point. In one direction, a slightly weaker wind, the erosion rate drops, and the planet might keep a thicker envelope for longer, but then you have to explain how you expose such deep helium-carbon layers in the first place. In the other direction, a slightly stronger wind or a slightly smaller orbit, and the stripping could accelerate, leading to runaway loss. Once enough of the remaining mass is removed, the gravity well shallows, making it easier to strip even more, and the planet rapidly transitions into a cloud of debris or a thin remnant. Right now, you're catching this system in the middle stage. The original companion star is gone as a recognizable star. The end state, a fully stripped or disrupted remnant, hasn't arrived yet. What you see is the in-between object, too processed to be a normal planet, not yet erased enough to disappear. It's literally living on borrowed time in a very narrow slot where the pulsar is strong enough to carve it down, but not quite strong enough to finish the job. And if that's the balance here, with a neutron star that happens to be on the low end of the power scale, you have to ask a bigger question. What does this system say about all the clean, colorful diagrams you've seen of habitable zones and safe orbits around tame stars when the universe is clearly willing to build and preserve nightmare worlds right next to stellar corpses for billions of years? How much of your tidy picture of where planets live survives after you look at a place like this? How much can you really trust those clean, green, habitable zone rings you see in every space graphic, when the universe is out here building gas giants next to neutron stars, raining diamonds and wrapped in soot? That's the hit this planet, PSR J2322-2650b, delivers to your neat picture of where worlds are supposed to be. Those diagrams with a calm star in the middle and a thin band where liquid water could exist on a rocky surface, are useful for teaching. They give you a quick sense of too hot, too cold, and maybe okay. But this planet is a reminder that they are only one slice of reality, and a very narrow one. Out here, you have a Jupiter mass object at about 0.010 astronomical units from a neutron star, roughly 1.6 million kilometers, around 1 million miles away, being stretched, cooked, and chemically rewritten. No tidy green ring covers that scenario. If you restrict your thinking to habitable zones around quiet, sun-like stars, you miss everything like this. You miss the gas giant with a helium-carbon atmosphere, soot clouds, and possible diamond rain. You miss the fact that atmospheres can exist and stay structured in radiation fields you'd normally call lethal. And you miss the message that the universe doesn't organize itself around your desire for simple diagrams. It puts planets wherever physics allows them to hang on, even for a while, including places that make no sense from a life-centric view. Once you accept that, the next question is simple but uncomfortable. If this planet can survive here, where else have we been underestimating what a planetary system can look like? Look back at how exoplanet science evolved. First, we assumed other systems would be scaled-up versions of the solar system. Small rocky planets inside, gas giants far out, more or less circular orbits. Then we found hot Jupiters hugging their stars at a few million kilometers, gas giants doing 3-day orbits. That already broke the old model. Next came super-Earths and mini-Neptunes packed close in, resonant chains, worlds and orbits we don't have here at all. Now you're dealing with planet-mass objects around neutron stars and white dwarfs in orbits that should have been destroyed when their stars exploded or shed their outer layers. You've got this planet next to a millisecond pulsar. You've got planets around white dwarfs where the host star has already gone through a red giant phase. Some of these planets probably formed after the main event, from leftover debris. Others, like this one, look like survivors or remnants. The takeaway is straightforward. If planets or planet mass remnants can exist here, you have to assume they can exist almost anywhere you can maintain gravity and not instantly vaporize everything. Disk edges, post-supernova debris, tight binaries, circumbinary orbits, even in dense star clusters, the universe will try every combination. Your job isn't to guess where it's allowed and then only look there. Your job is to look and see what actually forms and survives. That leads to another important distinction you have to make in your head: habitability versus survivability. This planet is never going to host liquid water oceans and life as you know it, but it survives, and that survival tells you something valuable about what extreme environments do to matter over time. In the classic picture, you focus on whether a rocky planet can hold liquid water on its surface at moderate temperatures. That's habitability in the narrow sense. By that metric, this planet fails instantly. Its day side is over 2,000 degrees Celsius, hotter than many stars. Its night side is still around 649 degrees Celsius, hotter than a pizza oven. The atmosphere is helium and carbon, missing oxygen and nitrogen in any useful amount. Radiation levels are brutal. There is no scenario in which this counts as habitable in the liquid water sense. But it is survivable in a way we didn't plan for. It keeps an atmosphere in a place where you'd expect any gas to be ripped away. It maintains structure, chemistry, and dynamics over billions of years while sitting deep inside a pulsar's radiation field. That matters, because when you search for life, you also need to know the full spectrum of what non-living but complex planetary environments look like. You want to understand which setups instantly destroy worlds and which ones warp them into something extreme but stable. Warped monsters like this planet. That knowledge feeds back into how you interpret signals from more moderate systems. If you see certain chemical patterns or temperature structures elsewhere, you'll know whether you're looking at a warped monster case or something closer to a potentially habitable environment. And this doesn't just influence your mental diagrams, it feeds directly into how telescopes are aimed and missions are designed. If planets and planet-like remnants can survive around neutron stars and white dwarfs, what does that do to your search strategy? Every time Webb or any next-generation telescope finds something this extreme, it forces mission planners to broaden the menu. Instead of only targeting sun-like stars with Earth-like planets in the habitable zone, you start to seriously consider dead and dying stars as targets too. White dwarfs with debris disks, neutron stars with timing irregularities hinting at companions, post-supernova remnants with dusty rings. All of those become more interesting. Not because you expect ocean-bearing Earth twins around every white dwarf or pulsar, but because these systems push your atmosphere models, your radiative transfer codes, and your understanding of chemistry under stress. A planet like this is a stress test. If your models can handle a helium-carbon atmosphere with soot clouds and possible diamond rain under a pulsar wind, you can trust them more when you apply them to quieter, more life-friendly systems. If they fail here, you know you have work to do. This planet becomes a flagship example of that shift. It sits in an environment that looks completely wrong from a basic habitable zone diagram, yet it's one of the most informative targets you could pick if you care about how extreme physics shapes worlds. It tells you that your search space for interesting planets isn't just the thin green ring around calm stars. It's the whole range of places where gravity can hold onto a body long enough for something complex to happen. And once you accept that, there's one more uncomfortable step. If the universe is willing to keep a planet mass remnant alive right on the edge of a neutron star's kill zone, slowly stripping it, stretching it, and heating it, you have to ask how this story ends. Is this world going to hang on like this for the rest of the pulsar's life, or is it already on its way to a final, slow destruction, spiraling in until tides and radiation finally rip it into a ring of debris? How long can this planet keep doing this before gravity and radiation finally finish the job? And what does that ending actually look like? You're not looking at a stable setup here. You're looking at a slow death in progress. And the key is that nothing about this orbit is truly static. Right now, this planet, PSR J2322-2650b, sits at roughly 0.010 astronomical units from its pulsar, about 1.6 million kilometers, close to 1 million miles. That distance already puts it on the edge of the Roche limit, where tides are trying hard to tear it apart. But over very long timescales, tidal interactions don't just distort the planet, they also change the orbit itself. The basic idea is simple. The planet and the neutron star are pulling on each other. The planet raises tiny tides on the neutron star, and the neutron star raises extreme tides on the planet. Whenever there's tidal distortion plus internal friction, some orbital energy gets turned into heat. You see that as internal heating and lemon-shaped distortion in the planet. But the energy has to come from somewhere, and that somewhere is the orbit. Lose orbital energy, and unless something else balances it, the radius of the orbit shrinks. Not fast, not on human timescales, but over millions to billions of years. You shave off kilometer after kilometer from that 1.6 million kilometer separation. Each small drop makes the tidal forces stronger, which creates more heating, which can lead to more angular momentum transfer, and the loop continues. At some point, if this drift inward continues, the orbit crosses the Roche limit. Beyond that line, the neutron star's tidal forces overpower the planet's self-gravity. The outer layers are pulled away more strongly than they can be pulled back. Instead of a single squashed body, you start to get streams of gas and fragments stripping off along the orbit. The lemon stops being just stretched and starts coming apart. If and when that happens, what's left doesn't just vanish, it reorganizes. So the next question is, what does this planet's death likely leave behind around the pulsar? The most likely outcome is a ring or torus of debris, a belt of gas, dust, and maybe larger fragments orbiting in place of the planet. The same gravity that pulled the planet apart keeps the debris in orbit at least for a while. Some of that material might slowly fall inward onto the neutron star. Some might spread out into a wider disk. In infrared, that debris would glow. Dust grains heated by the pulsar's remaining energy and by friction in the disk would radiate at wavelengths Webb and other telescopes can see. Instead of a single periodic brightening as a planet's dayside swings into view, you might get a smoother, continuous infrared excess from a warm ring. If larger clumps form, you could see small dips and spikes as they pass in front of or behind the neutron star from our point of view. In other words, the planet's destruction becomes the next experiment. The system's light curve and spectrum change character. Future instruments, maybe long after Webb, could look at that pattern and reconstruct that a planet-mass object once orbited there before being shredded. The final form isn't a dramatic explosion. It's a gradual reconfiguration into a ring of shrapnel, a belt that quietly documents what used to be a star, then a planet, now debris. While all of that is happening, the central object isn't standing still either. The neutron star is spinning down, very slowly, but inevitably. So you're not just watching the companion fade, you're watching the engine itself wind down. Every pulse you see from the pulsar is the star losing energy. The spin period creeps longer, millisecond by millisecond over long times. As that happens, the spin-down power drops. The particle wind weakens. The magnetic field structure can evolve. The high-energy beam that once blasted the companion and lit up our radio telescopes gradually fades. At some point in the very distant future, the pulsar may become so weak that its beam slips below the threshold of what we can detect, even with sensitive radio telescopes. It doesn't stop existing, it just becomes a quiet neutron star, cold by stellar standards, with a strong but less active magnetic field and a faint residual glow. If the planet has already been torn apart by then, what's left is a compact object with maybe a thin, cold ring of dust or rock, a kind of fossil belt marking where the companion once orbited. That final state is not dramatic in human terms. There's no huge flash announcing the end. Instead, the pulses get weaker, the debris cools down, and the whole system slips into darkness on the timescale of tens of billions of years. No more pulses, no more lemon-shaped planet, just a dense core and whatever rubble managed to survive the whole process. It's like the gravestone of a system that was once violently active. And that puts your current view of this system into perspective. Right now, you're catching this planet in a short, violent middle phase. It is no longer a normal star. It has already been stripped down to roughly Jupiter's mass. It's been reshaped, reheated, and chemically transformed into a helium-carbon object with soot clouds and possible diamond rain deep down. It's not a tidy ball near a friendly sun. It's a stellar corpse glued to a compact star and distorted until the word normal stops being useful. And if this one system can break your sense of what a planet is and where it can live, there's one final step. You have to ask what that does to your overall sense of normal in the universe, and how a single object like this can permanently lower your confidence in simple stories about calm, well-behaved planetary systems. How normal can you honestly think planets are after you've just walked through a world like this? You grew up with a very simple picture. Planets are mostly round, they orbit calm stars, they sit in neat distances that you can draw as circles on a page. This planet is your notice that the universe does not care about that picture at all. Here, you have something with roughly Jupiter's mass that is very likely the leftover core of a former star, held in a 7.8-hour orbit around a neutron star only about 10 to 20 kilometers across, roughly 6 to 12 miles. The host is basically a city-sized ball of ultra-dense matter. Tidal forces stretch this planet so hard that its equator is thought to be about 38% wider than the distance from pole to pole. The atmosphere is helium and carbon heavy, with almost no oxygen and nitrogen, wrapped in soot and probably feeding diamond formation deep down. It's not a tidy ball near a friendly sun. It's a stellar corpse glued to a compact star and distorted until the word normal stops being useful. So the old categories you learned, planet, star, habitable zone, were never promises. They were just first drafts. And the obvious follow-up is, if this is what you get as soon as you look next to a neutron star, how much else out there is quietly breaking those first drafts too? Every time the James Webb Space Telescope points at something like this, its real job is not to pat our theories on the back, it's to attack them. This planet is a perfect example. Before data, you'd say, okay, tight orbit around a compact object. Maybe it's a hot Jupiter analog. Hydrogen and helium, some water, some carbon monoxide, very hot but basically familiar. Then Webb hands you a spectrum that says helium and carbon, almost no oxygen-bearing molecules, very little nitrogen signature. Dayside hotter than many red dwarf stars, nightside still hotter than molten lead, soot haze in the sky, possible diamond phases inside, wind pattern possibly running backwards relative to the spin. That is not a gentle update. That's a list of ways the system contradicts your default expectations. Your migration models don't like a gas giant forming that close in. Your disk chemistry doesn't like losing oxygen and nitrogen that completely. Your atmospheric models don't expect the helium-carbon mix with that kind of heat redistribution. Your climate intuition does not expect the cool side at about 649 degrees Celsius, around 1200 degrees Fahrenheit. And Webb is basically sitting there saying, this is what's actually there. No story you tell can change the spectrum or the phase curve. If your theory can't handle this kind of object, the theory has to move, not the data. That's why this planet is so useful. It pushes you straight into the parts of parameter space where your confidence is weakest. Once you see how much it takes to break your models, the next step is to ask how you even get this level of detail from something that, in the telescope, is just a point of light about 7 quadrillion kilometers away, around 4.4 quadrillion miles. All the numbers you've been hearing, orbital speed about 350 kilometers per second, roughly 780,000 miles per hour, a radius stretched by about 38%, dayside and nightside temperatures, helium-carbon atmosphere, soot haze, possible backward winds, come from two main data streams, radio timing and infrared measurements. The pulsar's radio beam is like a clock. By timing the arrival of those pulses very precisely, you can see tiny delays and advances as the planet orbits, which locks down the orbit and mass. Then Webb steps in with infrared. It stares at the system for at least one full 7.8-hour orbit and measures how the total brightness changes over time. That gives you the thermal phase curve, which tells you how hot different sides are and how fast heat moves around. On top of that, Webb splits the infrared light into a spectrum, into hundreds or thousands of wavelength bins. Each dip or bump in that spectrum is a fingerprint for a particular molecule or particle type. So from timing, you get the orbit and the basic mass. From the phase curve, you get the temperature distribution. From the spectrum, you get the composition and some hints about cloud or haze properties. Combine those with physics you trust, like how gases absorb light or how tides work, and you build a consistent physical picture. You're turning 1 pixel's worth of data into a mental model of a real place. A distorted gas body, intense tidal stress, a helium-carbon atmosphere, soot clouds on top, likely diamond layers inside, strong winds, constant erosion. That's not guesswork. It's a chain of inferences anchored at each step to something you can actually measure. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.